Recording here. So, like I said, I'll do the match pairs case, and then we'll talk tech assignment, and then we'll go from there. So, when you're testing claims about two population means, there's two ways you can do it. One is with independent samples, and the other is with match pairs. It kind of makes sense based off of what what we were learning about in terms of the design of an experiment, that we should talk about the match pairs case, because that allows you to compare before and after scenarios. Right? I created a kind of a simplistic example. It's not really kind of meaningful in terms of real life applications unless you were really, really invested in the New York Giants in 1996. I was 18 years old at that time, so I was, but yeah, not too many other people were, because they sucked. Right. So match pairs are used when you're comparing before and after situations. Deals with one sample of subjects who are all given the same stimuli, and an effect is measured. Right. Then a little description of independent samples, but that's beyond what we're going to talk about. Right. You'll see that the assumptions are the same as they were for the t-test. You're talking about normal distribution, simple random sample. The one little extra bit is that you're dealing with a matched pairs scenario. Right. And how do you know it's matched pairs? You'll see the words before and after in the problem, or it'll be implied pre and post. Like this group of individuals had a measurement taken, and then later on they had another measurement taken. It'll be implied that it's the same group with multiple measurements taken. Right. So whenever you're conducting a hypothesis test, the first step is always to state the null and alternative hypotheses. We always want to state our alpha value, or determine what it is from the framing of the problem, then identify the p-value so that we can draw our conclusion. So the general shell of our approach is pretty much the same. And so, it begs the question, okay, so what's the difference? Well, the difference is that you're given two raw sets of data, right? So we have a little bit of background work that we have to carry out before we could get started on this, right? But once you kind of get the ins and outs of this, it's really not bad, right? First off, in the example, use a 0.05 significance level, right, to test the claim that there is no difference between the average New York Giants winning percentage before and after. So keyword before and, or key phrase, key term before and after indicates match pairs design. A bye week, don't necessarily need to know what that is in order to be able to evaluate the problem. Just before and after some event occurred between the 96 and 2004 seasons. All right. So we have our alpha value, which is 0.05. Now, no significant difference. That's a key component there. The average winning percentage is talking about a mean percentage, which is kind of weird. We're kind of mixing two concepts together. But no significant difference means the values are the same. Same as an equal. All right, so it's implied that our population means mu1 and mu2 would be the same as one another. All right, so what's happening is you had a winning percentage before this mysterious thing called a bye week. That winning percentage occurs over the span of, what was that, 10 years, 8 years, whatever. From that raw list of data, we have an average, we have a mean, and we have a standard deviation. Right? We also have a mean and a standard deviation for the after category. Right? What we're saying here is that, or at least the claim, is that there's no meaningful difference before and after a bye week. Right? Now, for those of you who are sports minded, even if you are sports minded, you may not care about this particular topic. But the reason why I selected this study I collected this data myself. It's all real data. It was because somebody made a comment during a broadcast, and that's usually what happens. That's my motivation for creating problems. You know, somebody made a comment during a Giants broadcast saying that this coach, I think it was the Philadelphia Eagles, Andy Reid at the time, he was notorious for, I can't remember which way it was. Like, he would always lose the game before a bye week and then win the one coming out of the bye week. It was something like that. It was like the bye week is a week off in a schedule, if you didn't know. Right. So you have a whole season of games, but then at some point in the season, you just get a week off. You get a week's vacation. Right. That they call that a bye week, like a bye week, you know. So you get to go away. So this coach and whatever team he coached, they always lost before the bye week and they always won after the bye week. It always kind of played out that way. And I said, I wonder what that's like for the Giants. I thought it was interesting. So I collected some information over a period of 8 to 10 years, whatever, you know. So, and I think if memory serves, it was the same coach. Maybe it wasn't the same coach, but it was like one or two coaches over this span of time. So that's why I selected this information. Right? There's probably more background than you needed, but you don't need that background in order to answer the question, right? So the null hypothesis always involves the equal sign. So mu1 is equal to mu2, right? So we got that claim. Now, we don't really have a sense of the alternative hypothesis here, right? So again, it says use a 0.05 significance level to test the claim that there is no significant difference between the average winning percentage before and after a bye week between the two seasons. So our possibilities are, you know, if we kind of think about it, what is the opposite of equal? Well, not equal. Symbol for that would be not equal. All right. So if we're talking about alternatives, the exact opposite makes sense as an alternative. All right. Now, I could say more, I could say less, and that depends on the data. But based off the distribution of this data, I don't really have a sense. You know, some values are more. So here in the before, it's more, but here in the after, it's more. You know, so the number that's the percentage is higher before in 96, but after in 97, after in 98, before in 99, after in 2000. I don't know what the breakdown is here. So what I would say is that my alternative is that there are simply some kind of difference, or there is simply some difference one way or the other between our two population means. I don't know what the difference is. I don't know if mu1 is more than mu2 or if it's less. I just know that it's different. All right. So the calculator test is still going to be a t-test. It's just how we're going to perform the t-test that's going to be a little bit different from what we did before. All right. So the way we handle this is by crunching the numbers. And I'll do it. I'll pull up a blank Desmos here. And I'll just type in the data.
Because it's not equal, does that mean this is a two-tail test?
It would be a two-tail test, yeah.
Cool.
And I'll get to that and how that impacts the p-value in a minute. Right, so let me get the calculator up here. So first I'm going to input the data. We don't need the years. So for a table, I'm going to do 0.4, you know, just get all the values in. 0.714. Oh, too many decimal points. That'll do it every time. All right, so I got all my information in. What I want to do here is find the difference between these two columns. All right, because if there's going to be a significant difference or no significant difference, we should probably figure out if there is a difference to begin with. So what we would do is we put this value, so we create a table. These values go into X1, these values go into Y1. And so in column 3, and some people like to do this on Excel or Google Sheets. It works just fine there too. So in column 3, type X1 minus Y1. All right, so X1 minus Y1. And it'll find the difference between all those values. All right. So when you hit enter, it locks it in, and you can get a quick look, and just at first glance, you can see if there's any kind of striking differences. You know, like for example, on the back end of it, you know, the bottom part of the list, I see 0.513, 0.618. That's a pretty significant difference, and it doesn't seem to be balanced out by any values in the negative region there. So we could be looking at a case where, you know, maybe there is a significant difference, but we want to carry out the hypothesis test in order to see for sure. All right. So now what I need is the mean and standard deviation of this. All right. So what we do is we call that the mean difference, the mu sub d and the sigma sub d. Well, actually, in this case, it's x bar sub d and s sub d, because it is for a sample. All right. So what we're going to do in a new line, function stats, we're going to find the mean, and that column has a heading. I mean, it's kind of annoying to have to do this, but the heading of the column is what you type in under mean. So X1 minus Y1. And it'll compute the mean of all that information. So we never really had to create the column to begin with. I just wanted to do that so you had an idea, so you'd be able to see what we're, you know, like what the distribution is. But, oh, dang it, Washington won. Oh, they're about to anyway. Oh, I committed a cardinal sin. I apologize. Like, I don't know who watches what. And like yesterday, I spent the whole day telling people if they told me the Giants score, I'd literally like rip their faces off because I was watching it on delay. I had a DVR. So, and I just flat out did the same thing. So I apologize. Anyway, so fraction value if you want, just so you don't have to deal with rounding. I mean, I don't think that's very appealing, but I'll write it anyway. I mean, we're going to get stuck with a decimal once we get to the standard deviation anyway. So you kind of look at this and say, well, what are we doing here? You know, like, why are we even bothering? So 0.087, and that wasn't like an existential thing. That was just related to this problem. So that's the mean, the standard deviation, again, of X1 minus Y1. We're talking about 0.331.
All you did here was you set your table, then you entered mean of column minus column and standard deviation column minus column, right? Because yesterday it kicked up and it was like, this is an X element array instead, but I may have done something wrong. So I'll look again.
Yeah, but that's all it is, yeah.
All right. I probably, it's because I did variable equals, and then it tried to return that the variable is actually an array. So
that's gotcha.
That's my mistake.
Okay, so we have a mean, we have a standard deviation, and we have a formula that allows us to come up with a t statistic, a t value, like we talked about last time. So what we did was we found the mean and standard deviation of the differences. So we basically we took two columns of data and made it into one column. All right. So what we're going to do as a formula for our t statistic or our t value it's basically the same formula as last time. T is going to be equal to, except instead of x minus mu, it's going to, sorry, x bar minus mu, it's going to be x bar sub d minus mu sub d over, I didn't really give myself much room here. I didn't give anybody really much room. Over s sub d over the square root of n. All right. So we got our x bar sub d, which is 0.0873. The mu sub d is the weird one. People don't really like this one, but if you really kind of talk it out to yourself, it'll make a lot of sense, because mu sub d is talking about the difference between population means. If the population means are assumed to be the same, then that value should be 0. Now, what a lot of people hear when I say that is, okay, mu sub d is always going to be 0. Okay, good enough. But there's a reason for that. And again, it's because there is no difference between two values. If there's no difference between two values, that means the difference is 0. If I tell you that there's no difference between my age and your age, I'm saying our ages are the same, which means if I took my age and subtracted from it your age, or vice versa, I would get a result of 0. All right? That's all that's happening here, and that's where that 0 comes from. All right? The rest is just plugging and chugging away. So we got the 0.331. And the n value is the number of pairs of data, right? So if you just kind of count them all up, I mean, you could look at the table too. You know, count it up in Desmos, or you just count it up here. This is my first, second, third, fourth, fifth, sixth, seventh, eighth, ninth pair of data. So we have 9 pairs ignoring the years. So over the square root of 9. So we crunch these numbers, and that gives us the t statistic. So 0.0873 minus 0. Well, let me do that as a fraction first. 0.0873 minus 0. You don't really have to write the minus 0. I'm just doing it for consistency. 0.331 over the square root of 9. And so we get our t statistic of 0.791 approximately. All right. Now, we need to come up with a probability value from this, which is the trickier part. Trickier? Yeah, that's part of it. Part of the fun. I'm just going to kind of chuck this over here. I had this great idea last semester of revising my notes so that I'd have these little flow charts in here. And all they do is take up room now. They don't really help. So I think I'm going to have to like undo my edit here. So anyway. So we have our t value of 0.791. We want to determine what that corresponds to in terms of a probability. All right. So we have a not equal symbol, and I'll just make a little note of that here. Mu1 not equal to mu2. That's our alternative. What that means, it's really kind of a combo. It means mu1 is greater than mu2, or mu1 is less than, that's not a 1. Ooh, is less than mu2. All right, either of those would fall into that definition. All right, so if I say my age is different from yours, but I don't give you any more detail, then you could say, well, it's either more than my age or less than my age. You know, like, you didn't really tell me anything. I just know it's not the same. All right. So what that tells me, based off of the normal distribution, I'll just draw a quick sketch here, is that this one could be on either side. All right, so, oh boy. So the T distribution is centered around 0 based off of the degrees of freedom, which we'll handle in a second. But that 0.791, if I label up my graph in terms of increments of 1, 2, 3, 0.791 would be about right here. Ballparking it. Here's 1, 2, 3. So if I'm looking at the case where mu1 is greater than mu2, I would be looking at this area. The issue is it may be going the other way, because what happened was we made the choice, right? And it's kind of weird to think about it this way, but we made a choice to subtract in order to find the difference between the two sets of data. We did x1 minus x2. We could have done, I'm sorry, x1 minus y1. We could have done y1 minus x1, in which case everything would have been reversed. So I'll make a little note of that. If we had did it that other way, then we would have gotten a different t value, negative 0.791. Okay, so reversing the order would have reversed the sign. So that gives us another possible interval. So t distributions end up being a little on the tricky side to begin with, but especially when they're two-tailed, because what I could be looking at is the probability that the t-score is less than negative 0.791 or greater than positive 0.791. Right? And we have to account for both of those. All right. So, cranky dinky. So we need to figure out the probability that t is less than negative 0.791 plus the probability that t is greater than positive 0.791. All right. Now, what a lot of people will do is say, well, it's symmetrical. So I can do one of two things. I could find the area in between the two and subtract from 1 because the total area under the curve is equal to 1. Or we could find double the probability that t is greater than 0.791. You can go either way. There's a bunch of different ways you can go. My recommendation, if you don't like the theoretical part of this, is to say, all right, well, if it's a one-tailed test, meaning the alternative hypothesis has a greater than or a less than symbol only, then you just use the calculator, Desmos calculator, to figure out the p-value, and that's it. If it's a two-tailed situation, you figure out the p-value, but then you double it. Right? So that's kind of a tricky little side application, but that ends up being a little bit easier for people to follow in terms of a process. Right? So I'm going to pull up the calculator for the student t distribution. And we're just looking, again, for the probability that we're north of 0.791. So my t min, well, with my degrees of freedom being 8, so n is 9. 1 minus that is, that minus 1, sorry, is the degrees of freedom. Although we don't really need that for this applet. Right. I'll get rid of this other one because it's kind of distracting. Just focusing on the purple. We're going again from 0.791 upward. All right, so I'll pop in the 0.791.
For degrees of freedom, don't you need to subtract 1 for degrees of freedom, or did you just say you don't do that?
We don't have to do it because I have it built into the formula.
Oh, nice.
All right, so I put in something big for the t max, and I see what the probability is there. If it's If it does, if I'm not sure, I just make that number a little bit bigger and see if that changes anything. I made it go from 10 to a 100. Either way, I'm going to get 0.226. So that's a little thing. 2 times 0.226 and so I'm going to take that number and double it. So we're looking at 0.5, what is that, 552? Actually, 452, something 52. Yeah, 452. All right, so that's going to be my p-value. And really coming up with the p-value, I mean, all these computations, that's the tricky part, obviously. I mean, you see all the stuff that we wrote down, but it's really for the purpose of being able to compare that to the alpha value, because if the p-value is less than the alpha value, then we reject the null hypothesis. Well, here's the alpha value, 0.05. Get a different color here. 0.05. That p-value, 0.452, yeah, that's not less than 0.05. 45.2% is not less than 0.05. All right. So if the p-value is less than the alpha, which it's not, I would reject the null. So I'm not going to reject the null. I'm going to keep the null, which means that I got to toss that alternative hypothesis. All right. So I'm going to write my conclusion with the idea that the null hypothesis is more true than the alternative. So there is, well, the first sentence addresses whether or not we reject the null hypothesis. So there is insufficient evidence to reject the claim that, and we state the null hypothesis in words. So mu1 being mu2, well, that came from the sentence that I have here. There is no significant difference between the average winning percentage before and after a bye week between the, that's a lot to write. I don't want to write all that. So I'll write some of that. The important points. There is insufficient evidence to reject the claim that there is no significant difference between winning percentage before and after a bye week. I'm just going to say a bye. All right. So there is insufficient evidence to reject the claim that there is no significant difference between winning percentage before and after a bye at the 0.05 significance level. Therefore, the claim, well, therefore what claim? They didn't really ask us anything else. But we needed the alternative in order to be able to carry out the hypothesis test. But they didn't ask us anything about an alternative. They didn't ask us whether it was more than or less than or anything other. So that second sentence would be, in this case, irrelevant. I'm just going to scribble that out. And the problem when we'll prep for the test on Wednesday, but I can tell you that the two questions, the two hypothesis test related questions are going to be very much like the ones that we've done in class. So they're not going to be, I'm not going to, mix it up, and I'm not even going to try to scribble that out anymore. I'm just kind of failing there. But what you see here is pretty much what you get. So, it won't be New York Giants winning percentages. It might be percent of people who, prefer chocolate ice cream to vanilla ice cream, something like that, and then, they have some sort of intervention, and then, they go to a conference at Hershey Park, and they're convinced that chocolate is the way of life. And so because of that, their percentage has changed. And so it's a before and after, you know, something like that. But you'll have a table and you're just going to pretty much reproduce this process, right? So as long as you know, I don't like saying it, but rehearse this approach, you're gonna get that question right. So in terms of new material, that's it for the course. So let me stop this recording so it's kind of a